received his PhD from MIT in 1998. Since then, he has been at University of Toronto.
Thanks a lot, Richard, and thanks for the invitation and give a talk here. So the title of the talk is Random Access Networks, Transmission Costs, Selfish Knowledge, and Protocol Design. So it's a long title, and it kind of illustrates the, I think, two main issues I would like to talk about, and I can come back to that later. So kind of the podcast has two parts. And okay, so what's the big picture? What are we interested in? So basically, the talk has been motivated by the popularity of the 802.11 protocol. Okay, people like to use wireless networks, and it's 802.11 is random access. Okay, and so there's still some difficulties to really understand what's going on in random access networks, and in particular with rate control and things like that. Okay, and so there's a lot of work going on on trying to understand 802.11 and also particularly TCP over 802.11. What I would like to do in this talk is to kind of be a little bit less specific, to just kind of take a step back and say, okay, if we have a random access network and a wireless random access network, and we want to do some resource allocation or some control, rate control, what are the issues we should consider, and what are the challenges? Okay. So maybe the next slide does make it that a little bit precise. Okay, I should also mention I give this talk for the first time. Okay? So it won't be that smooth, and if something is not that clear, ask me a question. Probably means I forgot to mention something or I didn't explain it clearly. So this is the situation. So we have a base station and we have different wireless nodes that want to communicate with the base station. Okay, and the problem is if two laptops send at the same time, the packets collide and they're lost. Okay, so we have some collisions. Packets that collide, they become backlog packets, and they have to be retransmitted. Okay, and so we know that. So this is stability issue. Okay, if you're not careful enough, then the number of backlogs becomes bigger and bigger and bigger, and the system becomes unstable. All right, and so you have, whenever you have random access, so you have to worry about, okay, how do we get around that? Okay. And one problem is the input. So you have to do different control, but somehow it's all right. And this is something we have to worry about. But also what is interesting, or we thought maybe is interesting or worth looking at, is that what is different in wireless networks from a wireline like the Ethernet, is that when so here you have a battery, okay? Whenever you send a packet, it costs you something in terms of battery power. Okay? So here we look at this random access network, or kind of one twist we add is that there's a transmission cost. So whenever you make a transmission attempt, it costs you something, which is non-trivial. And then the question we have is the following. Let's assume now we just let users do whatever, or nodes do whatever they want to do. Okay, so now you send your packets. Okay, and typically as the backlog goes up, you see more and more collisions. So if you see more and more collisions, and each transmission attempt is costly to you. Okay, so maybe you'll say, okay, now it's too expensive to send something, so let me reduce my sending. So the question we were interested in, if we would have a transmission cost, would it actually be enough to have stability? Okay. Or if we have a wireless network where users see some cost for transmission attempts, which become bigger when the backlog increases, is that enough so that we don't really need any rate control mechanism anymore, or is it not enough? So this is kind of where we start, kind of the twin random access networks with transmission costs. Somehow the intuition is maybe that helps us. Okay, maybe it actually makes life easier because it already implements a rate control mechanism. And the question is this true or is this not true? All right. So the next slide. I think that I made that a little. Yeah. So the question is a transmission cost, is it sufficient to guarantee stability? Okay. And if it's not sufficient, what kind of mechanism do we have to add? And the idea here is to add as little as possible. Kind of come up with a protocol that is as simple as possible. So you only add something if you really need to add something. Okay, so these are the kind of the questions we were interested in. All right. And so here I give you the answers. Okay, I will elaborate a little bit how we get here. But one answer is it's not enough. The transmission cost is not quite enough to guarantee stability. And in particular, if the transmission cost is too low, that's what gets you into trouble. Okay, so yeah. And then you say, okay, what can we do? And then you can do different things. But because we talk about cost and transmission are going to look at is kind of a pricing mechanism. So where we charge some additional prices. And then we show when we augment, if we add that mechanism, which is one of possible mechanism, it has some nice properties, so then it can guarantee stability. And also what we can do is we can tune the system accordingly. So you say, okay, this is the throughput I would like to have, and this is the delay I would like to have. Now I can tell you, okay, this is how you should choose the price. And exactly you get that. So this is so these are the basic questions. That kind of is a flavor of the results that we get. So now for the rest of the talk, I try to elaborate a little bit how we get there. Okay, so this is the outline of the game plan. Okay, so we start with this. So you see, we start with this kind of game where each users they're free to send whatever they want to send, but they see this transmission cost. Okay, and so we want to analyze this situation as a non-cooperative game. And when for this, we make life a little bit easy. All right. So you will see, we look at the idealized situation. So we make some assumptions, which makes everything a little bit easier. All right? And the idea to do that is so this is a little bit having fun. Okay, we want to just get some intuition what's going on. So because of that, we feel it's okay to make life easy in order to understand what's going on. So this part is more to kind of get some intuition. And in order to do that, we kind of look at this non-cooperative game, and we look for Nash equilibrium. Yeah. And in particular, we also look at a simple case, like a special type like symmetric Nash equilibrium. And that's a little bit easier. And then also we add in a pricing mechanism and study that non-cooperative game under that pricing mechanism. But all of this is done kind of under an idealized situation. For example, one assumption we make that we have quite a bit of information about the system. And then in the next part, what I would like to do is to kind of take these results and say, okay, what kind of a protocol would that suggest that we actually could implement in a decentralized way by getting rid of these idealizing assumptions that we make. So these are the two parts. So we start out with the game of the simplified situation, and then we want to use this intuition to come up with an algorithm. And also what I would like to mention, so for everything that we do in order to analyze these things, what we are going to use is the Slaughter-Galois model. And the reason why we choose that is just that the notation becomes simpler, and the results that you get are very elegant, or simpler. Okay, where you can do exactly the same thing for CSMA CD. Okay, but it's just you have more terms and everything becomes messier, and it's less, it's yeah. So by doing this, life is easier, but we don't really lose much in terms of of generality. Does that make sense? Or? Okay. So I think the next slide I define more precisely with the model that we will look at. So we look at Slaughter-Galois. So here is time. The assumed time is divided into discrete slots of length 1. This is exactly the time it takes to transmit one packet. So all packets have the same length. We assume that packets arrive according to a Poisson process. And then every node gets a new packet. It waits until the next time slot starts, and then it immediately transmits the packet. If two or more nodes try to transmit at the same time, okay, you have a collision. So you only have a successful transmission. Exactly one node transmits. If two or more nodes transmit, then you have a collision. These packets are lost, and they become backlog packets. Okay? And backlog packets, they have to be retransmitted at a later time. And here we look at probabilistic retransmission scheme. So you retransmit packets in each time slot with some probability. And so this is what we also add here. We assume that each transmission attempt costs you something, and so that there's a cost gamma per packet and per transmission. And we assume that each packet costs the same amount of money. Okay. And for each node, it's the same. Okay. And also what we do here again to make life a little bit easier. So we assume there's an infinite number of nodes. And by doing so, one way is to motivate is, okay, you're interested in the case where there's a large system. Really, also what it does, it makes life easier in the sense that if you have an infinite number of nodes, each node can have at most one backlog packet. So you don't have to worry about queuing and all that. So the analysis it's simpler. Does that make sense? So here I assume you have seen something like that. before. So okay. So this is kind of the rough. I have to be a little bit more precise. So I have to define a little bit more precisely what's the arrival rate of new packets. So here we assume the packets arrive according to a Poisson rate. Okay? So it's the aggregate rate lambda of u. And so here the idea is that our packets can have different values. So when you get a packet, if you want to transmit something, maybe this transmission has a different value of u. And u, that's the value of the packet. And so the interpretation of lambda of u is the rate at which packets arrive that have a value u or larger. So it's like the rate that not arrival rate of packets with value u, but of packets with value u or larger. Okay. And the assumption is that as u goes to infinity, okay, then you don't have any packets that have infinite value. So the arrival rate you go to 0. So here that's something we model. So packets have different values. And then also what we assume is, okay, this is now an idealized assumption, that nodes actually know the system state, or more refined, they know what's the current number of backlog, the total backlog packet in the system. And that's not realistic, but that's the assumption we make for now. Okay? And then, so what a node can do, it can observe the state of the system at the beginning of a time slot. And then it can decide, okay, when I got the new packet in the previous time slot, should I accept the packet and try to transmit it, or should I drop the packet? So here, that's one decision nodes can make. Should I accept the packet or not? And probably you assume, depending on the value of the packet, maybe you make different decisions. Okay. Once you have accepted the packet, you know, it's it becomes a backlog packet, and you have to retransmit the packet. Another what nodes are free to decide, they can see what's the state of the system right now, and then they can say, okay, with which probability should I now transmit the packet? Okay, so this is kind of the decisions that the nodes can make in the non-cooperative game that we look at. And so how can we? So we can then kind of formulate this decision using a strategy which has two components, u and q. Okay. So u tells you, okay, at state, so it's a vector at state 0, 1, 2, 3, or so on. What's the value of packet that a packet has to have in order to be accepted? So u that tells you u1 is the minimum value that a packet has to have in order to be accepted if there's currently one backlog packet. Okay, so that's this decision here. The other decision here is if there are 1, 2, or 3 backlog packets in the system, what's the probability with which I will transmit the packet? Okay, so this is how we define a strategy. And we also use this formulation here as a strategy, lambda on q, where at state n, lambda of n is just equal to the arrival rate under the value u. So there's a little bit of use of some case to make it kind of a little bit simple. Yeah?
What exactly is the interpretation of this value of packet?
No, it's more an application, okay? You know, let's say maybe you run different applications.
Is it something like utility assigned to any common packet?
You could translate that into a utility, but somehow it's almost like a value. It's just say, okay, if I could transmit that packet, what kind of a value would that be to me?
It would be like quality of service.
Could be quality of service, or could be, let's say, you know, maybe you run different applications and someone is like sending an email that's not that important. I mean, there are always these examples that we.
And who makes this value?
Excuse me?
Who makes this value?
Oh, it's like you personally. Okay. So let's say you send. Let's say there are a couple of packets you have to send. Okay. And I tell you you're only allowed to send one. Okay. Maybe you could say, okay, this kind of is the most important. That's the one I would have to send. Okay. And then I say, okay, you have to pay for it. How much are you willing to pay? I said maybe you could say, all right, if I have to pay less than that, then I will do it. So that's the idea. So you have a bunch of packets, and somehow, personally, and only you, the node, knows that. Okay, they have different values.
So what's the domain of you? Integers, real numbers?
It's real numbers.
Real numbers.
Yeah, it's real numbers, yeah. Okay. Yeah. So you won't have complete functions. Other questions? Right, so this is kind of again, so what's the next? So now we want to do some analysis. So that's kind of the problem set up. Okay. So again, that's another assumption that we make. So we assume that all nodes are the same. Okay, so it's like a homogeneous system. And the reason why we do that, then we can look at symmetric strategy. So we can assume that everybody in the equilibrium, a good strategy would be the same for each student. So that for each node. So that allows us then to look at symmetric Nash equilibrium. Another one makes it easy if then also when you assume that all nodes use the same strategy, you can describe the system as a Markov chain, where n of k is the state of the system at k. Okay. And then lambda tells you, okay, what's the arrival rate of new packets, and q tells you, okay, what's the retransmission probability of backlog packets. Okay. And if you just look at the symmetric strategy, you just have to look at the one-dimensional Markov chain in terms of the backlog packets. Does that make sense? Okay. Right. And so this is, and then once life just becomes easy. For example, then you could ask, okay, let's say currently there are n backlog packets in the system, and I decide to retransmit my backlog packet. What's the probability that my packet will go through? It's equal to the probability that in the previous time slot, or that right now, the arrival rate of no packet is arriving that is getting accepted. So this newly arrived packet that is going to be accepted that joins the system. Okay. And also what I need is that all the other packets, so if I have a packet, I know n minus one other nodes also have a packet. They are not allowed to retransmit the packet. So if I condition that I make a retransmission attempt, this is then the probability that this retransmission attempt is going to be successful. And if Q is very, very small, we can make this assumption. This approximation here. Okay, it's kind of a standardized approximation that you use when you analyze Sloboda-Law. And also what we then can define is the offered load as a number of the backlog packets. It's lambda of n, is the arrival rate, plus n. Okay. So this is the average number of retransmission attempts that you see in the backlog. Okay, and then the instantaneous throughput, that's Sloboda-Law is given like this. Here to observe that this term is almost the same like this term, but not exactly. Here's the n minus 1, and here's the n, which makes the analysis a little bit tricky. Any questions to this? Okay, so that's kind of the setup. So we're now in the so this is okay. We have now a Markov chain set up, which allows us to analyze different strategies and say something about the performance and about the output. And so here I don't go into the details. So once you have a Markov chain, okay, and there's so there's whenever you make a transmission attempt, there's a cost, and when you are successfully transmitted the packet, you get the reward U. Okay? So you also can define on this Markov chain the Markov reward process, and you can then ask questions. For example, let's assume that everybody uses strategy pi, okay, and I accept the new packet at state n. What's the expected cost for successfully transmitting that packet? Or I can ask, okay, let's say that everybody uses strategy pi, and at state n, I have a backlog packet. How much, on average, do I have to pay in order to get rid of that packet? So you can define these quantities. Okay. All right. So this is, if you just look at one strategy, that's certain things I could compute and that are of interest. Okay. There's another situation of interest. Somehow we assume that each node tries to maximize, so we want to look at the Nash equilibrium. Okay? So we want to ask the question, let's assume that everybody else uses strategy pi, but now I change my retransmission probabilities a little bit. So I use a different vector Q hat. Okay? So everybody uses pi, but only I use Q hat. Okay? What's then the cost for me to successfully transmit a packet that I set and state n? Or everybody uses pi, I use Q hat, and I have a backlog packet at state n. What's the cost, expected cost to get rid of the packet? Does that make sense? Yeah?
I didn't see where you introduced the cost.
So the cost is whenever you make a transmission attempt, it costs you gamma.
Oh, it's fixed parameter.
Yeah. I said that each packet has the same cost gamma.
In terms of gamma, how is the O and the Q?
Yeah, I mean I have to write the. I didn't want to write all these things down, but once you have a Markov chain and a Markov process, something like this, I mean, these are things you can define and compute if it's well behaved.
So you need the sum of
Exactly, yeah. And it's the expected value. Okay, condition that you start at state n. Okay, the sum. Okay, the cost at the different states. Yeah, I mean, you have to here I skipped, so I didn't give you the transition probabilities of the chain at same time, so I kind of wanted, yeah.
Is there a reason that the cost for transmit a new packet is different from the cost to transmit the backlog packet? Except the information that a new packet is accepted.
Okay.
Or
Yeah, that's the difference. That's the difference. Okay. I didn't write that. Where was it? Here. This is the probability for a successful transmission for a backlog packet. If you compute this probability for a newly accepted packet, it would look a little bit different. So if this would be the same for a newly, then problem would become much easier. But actually, here you would have to condition that I'm the only one who received the packet, and everybody else doesn't have a retransmission. So these two things are different. Very good, yeah. So I can suppress that. Other question?
You haven't defined the policy. Are you talking about the optimal policies here?
No, I defined kind of the decisions you're allowed to make. Okay, you're allowed to define a state I, what's the value n, what's the value a packet has to have, and what's the retransmission policy. Yeah. So I kind of I defined what a strategy is. I didn't say yet what kind of a strategy I look for. Okay, I just say if I have a strategy, I can compute this type of. And I think the next slide comes back to what kind of strategies I look for. Okay, so here I have to be a little more precise of the type of strategies I look at. Okay, and so there's a. Okay, so let's assume now that everybody uses strategy pi. Okay, and let's say I now try to optimize my strategy, so I try different retransmissions for vectors q hat. Now we restrict a little bit what retransmission vectors you are allowed to use. You know, particularly we ask you to do is that once you accept the packet, you have to make a proper effort to transmit the packet. So what this means is, if I accept the packet at state n, everybody uses strategy pi. I use strategy or the retransmission vector q hat. Okay. When Tn is the kind of the time starting at the end, how long I wait until I make the first retransmission attempt of the backup packet. It has to be a random variable. Okay. So this basically tells you that the time between retransmission attempt has to be finite with probability 1. Okay, so you're not allowed to cheat and say, okay, I accept that packet, but they cannot, hide it somewhere and never retransmit it. So once you accept the packet, you have to commit that I make a proper effort to retransmit that packet, and the time between retransmission attempts has to be a random variable. So you cannot wait for infinite time or infinitely data reach. So this is and so this is what we call an admissible strategy or a proper strategy. You make a proper effort to retransmit it. Okay. And now if you have a strategy Q, you can look at the set of all admissible retransmissions. Okay. And then you can decide, okay, so now I can define an admissible strategy like that. Okay, so if there's nothing there, okay, you want that something enters the system. Okay? So at state 0, the arrival rate should be not 0. If it's 0, then you never get started. And also, if you have a strategy and you look at all the admissible retransmission vectors, Q should be part of that. So it's kind of, yeah. All right. So this is the restriction on the strategy you do. But this is the most important one. You have to make a proper effort to retransmit. Okay, does that make sense? And now I define, okay, what's kind of a strategy? So I look at the equilibrium strategy. Okay. So I say, okay, I fix the strategy pi. Okay. And now I choose a new retransmission vector over all admissible retransmission vector, and I look for one, okay, that minimizes the cost for successfully successfully getting rid of the packet, for at any state. And what has to be true that the Q, okay, of this strategy, that has to be the optimal solution. Okay, so basically you say if you have a strategy pi and you can change your retransmission probability, you wouldn't change it if you were at an equilibrium. That's what that tells you. Okay. And the other thing says is that like if you say, okay, I accept all packets, so this value has to be equal to the total cost and expected cost that it takes you to successfully transmit the backlog packet. So basically what that says, I only accept the packet if its value is equal or larger than the cost it is for me to transmit. And this we call an equilibrium strategy. And the reason for that is that if it satisfies this property, you can show it's a Nash equilibrium for the setup. So these are the strategies we look for. So basically we look for this non-conflictive gain. We look at of course, the symmetric Nash. Does that make sense? Okay, so that's all right. So we let use through and we look for a Nash. Well, we're interested a little bit more. Okay, we're not just interested in equilibrium strategies, but also we would like the system to be stable. Okay, and so here, kind of that expected number of backlog packets stays bound. So this, in the end, that's what we're interested in. We're interested in a symmetric Nash equilibrium that is stable. And the nice thing is when you look at it, somehow intuitively it makes sense. You would like to have a Nash equilibrium. Would like it to be stable. But once you have that, actually the underlying Markov chain has a nice property in the sense that there's a single positive recurrent class and possibly some transient state. So it's the underlying Markov chain has a very nice structure which you like to have in order to do some analysis. And this is only true when you have an equilibrium allocation that is stable. So particularly in order to get that, just being an equilibrium allocation is not enough, because if it's not stable, the states won't be positive recurrent, but they all will be transient. Okay. If you only have a stable strategy, it's not enough to get that. For example, if at each state you always stay here, okay, and you could stay here by not doing anything at all, or here with always retransmit with probability 1, so you always have a backlog. So something like this would be stable, but you can show, this cannot be an equilibrium strategy. Okay, so in order to get this nice structure of a single positive recurrent class and some transient, you need both. It has to be an equilibrium, and it has to be stable. So this is basically the kind of the setup problem formulation. And the question that you can ask, okay, that's what you're interested in. Does a stable equilibrium strategy exist? Is it unique? Okay. And can you say something about the performance in terms of throughput or delay on the stable equilibrium strategy? Does that make sense? More or less. Okay. I'm not sure whether I got too slow or too fast. Okay, well that's the question you want to ask. Right. So, but in order to do that, so how do we solve that? Okay. So if you think about the problem for some time, you have some intuition how a stable equilibrium strategy or how an equilibrium strategy should look like. Okay. And so the next slide kind of introduces a particular class of strategy which has some properties that make them kind of attractive candidates for an equilibrium strategy. Okay. So what we look at the class of states as a function of kappa, which is positive. Okay. And what we require that for this strategy. So it's a set of all strategies. So it has this property. So it's a class of states. Okay. So states which communicate with each other of this form. So there's an integer n0 and all states n0 or larger that belong to this class. Okay. So it's a nicely connected class which starts at some state and then comes on. Okay. And then I say if I look at the state in this class, okay, then this has to be true. Lambda of n is equal to kappa. So I say in the state space, so there's an integer n0 then all these states larger than n0, they communicate with each other. There's no other state outside that they communicate with. So that means once you're in that class, you stay in that class. And also what I say, for each state in that class, this is true. Why is this nice? Okay, maybe you remember that. What we said, okay, what's the probability of successfully retransmitting a packet? Okay, it's given like this. And if this is true, it's given like this. So kind of what that tells you is that each state in this class, you're equally likely to have a successful retransmission. So basically you're indifferent where you retransmit your packet. And that's what you need for an ASHEC to do. If that wouldn't be the case, okay, then you would favor the states where the retransmission probability is better. Okay, so that's the intuition that somehow in equilibrium should have these properties, that at all states you're equally likely to get rid of the packet. And once you have that, then you can compute the cost for retransmitting, successfully transmitting a backlog packet starting at state n. It's just given like this for a state in this class.
All this assumes you know lambda is a function of n plus least,
Yeah, we come back to that, exactly.
which you don't.
No, that's what I said. Okay, there are two, alright, let me put it. Okay, there are two things we assume here. We assume we can observe state n. Not true. Later on, we assume you know this function. Okay, not true. But let's just play around with it and see what we get and what we can learn from it. But that's what we should do. So this is the intuition. Someone is saying an equilibrium strategy should look like this. And once it looks like this, also one cost is very easy to compute. Okay. And then you can ask, okay, is this all, if I look at an equilibrium strategy, is it sufficient to look at these classes, or are there some other, strategies that are not included? So these are kind of the questions we want to ask. So first we ask the question, okay, if I give you a kappa, okay, does there exist an equilibrium strategy in that class? And so here is one result which says, there exists actually I'm interested in stable equilibrium strategy. There exists a stable equilibrium strategy in this class, if and only if these conditions are true. So here I didn't really derive. So here are some quantities I didn't really define. So the purpose of this is just if you ask the question, for a kappa, is there a stable equilibrium strategy? Some conditions have to be satisfied, and they're not always satisfied. Okay. So the idea here is, it's not always true that, give me kappa, that there exists a stable equilibrium strategy in that class. But some conditions have to be true.
What are these fr and r0?
Yeah, this is the thing, I didn't define that. So you have...
Will I be?
This is kind of, as n goes to infinity, the total cost for retransmitting a packet. So that means that...
What is What is it infinity? What is r infinity? What are zero? What type of animals are they?
Oh, this is a r infinity?
Yeah.
Okay, maybe alright. Okay, maybe so I defined this thing here. I think that's what I defined.
Okay.
And I say limit n to infinity. Oh, this is r infinity.
Okay.
And then here you see that asymptotically the arrival rate has to be less than the then how this is just the g e to the minus 2.
Yeah.
So this is kind of, here you see stability. This is kind of a function. This tells you that there is a fixed point at which the value so what you also want to show, you want to show that u of n equals r.
Yeah.
Okay. And this, in order, you can show that this is true if limit n to infinity.
What is f?
So this is kind of basically, this is the retransmission costs.
Okay.
It's kind of it's a fixed point equation, and you have to see does it have an equation or a solution or not. And this, so if you look at this function, and this kind of tells you, okay, it has an equation. So basically, I can tell, all right, a little bit. So you can tell that this function starts here, and then it's strictly increasing. And if it goes over, something, then you know that it's a fixed point. It always happens. So there's kind of conditions for this to get these things. But here the point was, okay, there are some conditions that they're not always satisfied. In particular, they're not satisfied if the transmission cost gamma is too small. If I could choose gamma I always could make sure that there exists an equilibrium. But I cannot control gamma. If gamma happens to be too small, it won't. So this is already tells you something, okay, the cost is not always enough to stabilize the system. Maybe there doesn't exist a stable equilibrium. Does that make sense? All right. Okay. But now let's ask the question, and what does that say? This tells you, okay, give me a stable equilibrium allocation, pi. And what I can then find is a class, as a function of kappa. So pi is in there. So this tells you that these classes of strategies, there are indeed sufficient to characterize all stable equilibrium strategies. So any stable equilibrium strategy has to be in one of these classes. So there's nothing. So these classes are really enough to look at in order to characterize stable equilibrium strategies. Okay? And once you have that resolved, okay, then there's certain things you can say, okay, because it doesn't, for this class, it also doesn't always exist stable equilibrium. So then you can say, okay, if the cost gamma is too small, then maybe there does not exist a stable equilibrium strategy. Because that's the answer. Transmission cost is not always enough. If it's too small, it's not enough. Okay? The other thing is, once you have I
just wanted to ask, is there some condition for how large the transmission cost needs to be?
Oh, you could get something like this. Yeah. Oh, that's exactly, I come back to this. If you give me a kappa and all that, I tell you, okay, there's a gamma maybe. That's the whole point. By making gamma large enough, I can guarantee that there is one. But I don't have control over the gamma. But now that's the next step. Okay, let's assume how could you do that? You charge some additional cost, and you choose this cost. That's the whole idea. Okay, you want to make the gamma large. Other question? Right. So there isn't always one. Okay, if there is one, okay, so that means there is a kappa. Well, kappa is a continuous. If there is a kappa for which there exists an Nash equilibrium, typically there's a whole range of kappas for which the conditions are true. So typically there's a continuum. So if you have one, typically you have a whole lot. Alright. And also, depending on kappa, okay, it gives you different performance. So once you know kappa, it dictates a little bit what's there. For example, here, maybe I mentioned this. Okay. The kappa gives you an upper bound on the sustainable throughput that you can get. Okay, so if you give me kappa, I know what's the maximum throughput the system can have. So the idea here is different choices of kappa will lead to different systems performance. And even if there is an equilibrium, okay, maybe you don't know which one the players are choosing. So maybe typically there's a good choice, a good equilibrium and a bad equilibrium. But you don't know which one in terms of throughput. Question to this? You peek ahead. Okay. So this is basically, we did the analysis of this game, and there is this result. Okay, there's not always maybe that's what I think I said that here. So now you can say, okay, we learned something. What does it mean for protocol design? Okay. So we know now the transmission cost is not enough to get stability. Okay. So somehow we need something additional to guarantee stability. Okay. And also somehow we would like to have a mechanism which enforces a certain kappa, because kappa dictates the performance of the system. Okay, so how could we do that? And so like you said, okay, in order to make it stable, what we have to do is we have to increase the cross gamma. So what we could do is to just charge nodes and additional cost C for each successfully transmitted packet, and these costs could be charged at the base station. Okay. And once you do that, you can guarantee there's always.
If I plot K equals minus, if I plot K times e to the minus K, which is the throughput.
Yeah.
That has a maximum.
Yeah, exactly. Yeah, it's just solid alone.
So
yeah.
why don't I pick the maximum K star for that?
Yeah, that's what you want.
Okay.
K equals to 1. Yeah. Yeah, exactly. Yeah. I mean, yeah, that's what it boils down.
Okay.
Yeah. But so here the idea is, okay, if you have all this information, all right, so I can choose C to always stabilize the system. I can choose K to kind of set the performance, all right. And so basically I can do more, okay. If I can design the system very carefully. So if you say, okay, there's a certain throughput in the delay, but of course there's some trade-off. Okay, there's somehow.
Do you have an expression for delay in terms of K?
Not nice, but intuitively, okay, the closer you get to that, the delay will go.
Can you compute the trade-off curve? for
We didn't try. Yeah. Here, just say there's not complete freedom. I want to have very low delay, very high throughput. Okay, there's some coupling there, but we didn't look at that. But the idea here is that there is a curve, okay, and you can choose where you are on the curve. Okay. All right. So if you know everything, and if you could choose, you could actually really design the system very, very nicely. Okay. So here the idea is that the C, okay, if you have all this information, choosing C is not that hard. The question is, okay, how do you enforce that kappa? Okay. So here's what the hand wave is. So here what I say, let's just assume, you could create an even net card or a 8.2.11 card. Okay, and you have all this perfect information. Right. And somehow you say, okay, which kappa should I choose? And as John mentioned, it should be kappa equal to 1. Okay, you choose kappa equal to 1, then you choose a certain C to get the throughput delay that you would like to have. And once you have kappa and C, then you can actually, you know everything, okay, arrival rate and everything. You could compute the retransmission probabilities Q of N. Okay. So what you can do then is to code this Q of N into your card. So basically you standardize the protocol. Okay, this is the card you sell. And now you ask if I sell this card like this, are users going to hack it and change the retransmission probabilities or not? And the answer is that they won't, okay, because it's a Nash technique. They have no incentive to do it. So somehow it's like a cheat proof MAC protocol because it implements a Nash technique. And then you could say, okay, here standardization would make sense because nobody has an incentive to deviate. And I think was there a talk in the fall by Jean-Pierre Ribaud about cheating and things like that. So in this case, it's not an issue because you have a Nash.
But can two nodes cheat together?
Oh yeah, no collusion. No, we didn't look at this. Yeah, you assume everybody is independent. Yeah, of course. Yeah. So in this scenario, there would be no problem. Okay. So here's the idea: is okay. It tells you something about protocol design. So somehow you would like to be able to standardize the demand in a way that nobody cheats. Okay, and then you kind of want to choose these value C to get a certain throughput. So here's the first part finishes. Okay. And the idea is we learned something. Okay.
Yeah, to what extent will this result be depending on the knowledge of N?
Oh, very much.
The system, very much?
Very much.
If I only look at my local knowledge of N, because I am a one node, I have no idea about it.
Yeah.
So that will break at all?
Yeah, everything I talked about will break.
Well, everything will break.
Everything will break.
Why?
Oh, because you have to know, okay, in order to...
Not necessarily.
Well, if I don't land of you, I can't...
Because of the way you try to prove it, that you use states. I mean,
yeah.
What if I insist that the meaning of K is in the same? In other words, I don't want anybody to have any different probabilities of retransmission. Why do I look at it this way?
Yeah. So, okay, you ask a question. The answer is yes. All the results I got here depend on this lambda.
Right.
But the next question is this final, or can we overcome that? And the question is yes, you can overcome it. And that's the second part. Okay.
Oh.
Now, in the second part, I want to drop this assumption that we know this. And I kind of say, okay, can we come up with something that we actually...
Because that will be more applicable in the real world. That will be more applicable for, say, work.
Yeah.
Or any distributed.
Exactly, yeah. But here, here the intuition is, we want to set this cost C. If you can set this cost C, that's all you need, okay? Gamma is not always enough to get stability, okay? So somehow, you have to make gamma large enough. What's the most natural way to do that? To add another price C. And now the next thing is I'm going to look at is at the pricing, a price-based rate control, where I drop this assumption of we know lambda. Okay, but that's the motivation. So the next thing I want to do, I have a little bit of time. Okay, these were these assumptions which are not true. So the question is, can I come up with a rate control, a price-based rate control, which doesn't use these assumptions? And so the idea is you only have local knowledge. Okay, what's local knowledge? You can observe the channel. So you can see is it an idle slot, collision, or a successful transmission. Okay. And then you say, oh, I see. Somehow intuitively, if there's a collision, backlog packet, maybe I should increase the price C a little bit. If there's an idle slot, nobody uses it, maybe I should decrease. Okay. So this is kind of the intuition. Let's see if this would fly. So somehow we want to set a cost C but I don't know the arrival rate. Is there still a way to set this cost C? And then you could say, maybe this is an interesting approach. Okay, you just observe the channel, increase it, decrease it, and see what's going on. Okay, the question is, okay, is something like this, can it be stable? And can we say something about the operating point? Okay, can we say that's a throughput we would like to have? And so on. So that's the next question I would like to look at. Right. So here's again, so we have this price signal U as before, and U kind of, it modulates the arrival rate. By changing U, the cost that we charge, you have an influence on the arrival rate. And this is the intuition increase, decrease. Okay? So this is the price adaptation. So that, from time slot to time slot, okay, whenever there's an idle slot, okay, there's no retransmission. What we're going to do, we're going to decrease the price. Decrease the price, exactly. When there is a collision, okay, more than two or more arrivals, collision, we're going to increase the price. If there's a successful transmission, not quite sure what we should do. Maybe we should just leave it like that, maybe increase it, okay, we're not quite sure. So this is what we want to look at. So this is how from slot to slot, how we update the price according to the observation of the channel. Where we insist whether it's idle, we decrease it. If there's collision, we increase it. Data for now, we just leave it open. We can choose as we want it. Okay? And here we assume, okay, this is now here assume that the retransmission probability is fixed. It's equal to Q. And everybody uses the same data. And now we want to analyze this and see what we get.
Basically, the base station is setting the price.
That's the idea right here. Yeah. You will charge exactly an access charge at the base station. Other question? All right. So what do we get? Okay. So once you have now you have a two-dimensional Markov chain. So one is the number of backlog packets, and the other is the price signal that you have. And so we don't really know what this arrival rate is, but we assume that it's bounded. It's not bounded. You do. And also, if the price is large enough, it disappears. That's all we need right now. We can get off that a little bit later. And once you make this assumption, then you can say that this Markov chain is stable, is positive recurrent, as long as we know that alpha is less than 0, gamma is large. So as long as this is true, it's going to be stable. So this is all right. Stability is, without knowing exact the shape, as long as it kind of has this structure, stability is easy. And moreover, there's a lot of parameters of alpha and beta and gamma, for which the system is stable. Whenever gamma, all you have to make sure that this is less than 0, and this is larger than 0. So the next question is, okay, maybe can we choose alpha, beta, and gamma in a smart way, so that we can set the system performance? And I think that's the next slide. So we want to kind of look at the system's performance under a certain set of control parameters. And in order to characterize the system performance, we look at the operating point. So I say, okay, my current state is N and U. I look at the kind of expected one-step drift in the number of backlog packets, expected one-step drift in the price. And I say it's an operating point when this is equal to 0. The kind of expected drift is equal to 0. And the question is there an operating point? And is there a unique operating point? So these are the results. Stability we already talked about. So under some conditions, which are not that strong, there exists a unique operating point, N star, U star. G star, that's the offered load under the operating point. Now, once you know G star, you know a lot about the system. So once you know G star, you know the throughput. If I know the throughput, if I know the G star and the throughput, I know the retransmission probability, I can compute the backlog. Okay, and once you know, I also can compute the delay. So the idea here is once you have G star, you can characterize the performance of the systems at the operating point in terms of throughput and delay. So what we really would like to do is to set that G star. So the idea here is, okay, somehow I would like G star equal to be G0. Or like just some G star. Okay. So the question is, somehow I would like to choose a G star which leads to a certain throughput and delay that I like. How can I do that? And the answer is, you can do it, and actually quite easily. Okay, what you do is you just choose alpha and gamma arbitrarily. But alpha to be less than 0, gamma larger than 0. And then you set beta like this. And when you do that, you guarantee that the operating point. has this overload. So what I tell you here is that so you can decide by just choosing alpha, beta, and gamma, you can ensure that the overload at the operating point is G star, that this is the throughput, and this is the average speed.
So the G, let me understand this. You set alpha, beta, gamma, and then G star is determined by this equation?
Exactly. No, I choose alpha and gamma, right. And then I determine beta so that the overload at the operating point is G star.
How do you set G star?
No, I wish, that's my goal. My G star maybe should be equal to 1. Okay, that gives me maximum throughput.
Okay.
How should I choose alpha, beta, and gamma to achieve this? Okay, this is how you should choose it. Okay. All right, the nice thing here, there's no lambda. Okay, in order to do that, you don't need to know the arrival rate. You don't even need to know Q. Okay, so you can set it a priori without knowing anything about the system. And so this is okay. You can do it, all right, without knowing anything.
How fast you convert it?
And I will come to that. Okay. So this is kind of the result. Okay, so it's quite nice. Okay, you don't need to know anything, and you can a priori you can do it. What's the next thing? Okay, so here's the result. Okay, so what we want to do is G star. So that's the maximum throughput. So we really want to push the system so low to G star. So the maximum throughput is e to the minus 1. Okay. And that's then the thing, okay? Alpha, we just show, you see arbitrarily, minus 1. Gamma is equal to 1. We didn't put in a whole lot of stuff, minus 1, 1. Use this formula to get beta, that's what beta is. Okay. This is our arrival rate, lambda of u. This is how we chose Q. And so what you see, so here is the trajectory, so it's a two-dimensional Markov chain. You start at 0, 0, this is how n evolves. This is how u evolves. So you see there's a transient, and then you hover around this operating point. And okay, this is one example, okay. And so there's a trade-off, your question, there's a trade-off between variance and convergence time.
Because that was fix alpha and beta and something, because the iteration has three parameters.
Yeah.
So which one is the control?
What do you mean by put forward?
Okay, if I look at the iteration, the way you adjust your u, right?
Yeah.
And if I do the drift analysis, you can look at the eigenvalues, right? Of the iteration, right? Or if you don't like.
Oh, you mean about convergence speed, or?
Yeah.
No, we didn't do it. You didn't do it exactly.
That will reveal how.
Yeah.
Choose alpha beta gamma to get the convergence. I don't know if it doesn't.
Well, it always converges. Okay.
Sure.
Yeah.
The speed.
Yeah, the speed. We didn't do math. Okay. But it's kind of you see quite fast. The large. So you just can scale up. Let's say you have a solution. Alpha, beta, and gamma. Okay. The K alpha, K beta, K gamma will give you the same operating point. It won't change it. So you just can scale it. If K is larger than 1, you increase the speed, but you also increase the variance. If K is small, you decrease the variance, but you have to stretch it. So this is kind of a trade-off. It's easy to see, but we didn't do it formally and say, okay, this is.
In terms of actual times, well, what I'm getting at is the time to convergence.
It's quite fast. It's fine.
Is it appropriate for the way the protocol operates?
Yeah. I think so. Okay. So here is one thing. I don't know. Okay. One thing is how do you do it? Okay. If you want to do stability, you have to do something. You have to be adaptive. Somewhere adaptive. Here we adaptive at each time slot. At each time slot we change. Something else you could do is you kind of could estimate, kind of taking an average, an estimate of the average, and use that and things like that. And that will be much slower. So you have to be in here. That's almost the fastest you can do. At each time slot, you update.
But that happens at the hub, right? Because the hub adjusts the price.
Yeah. Then kind of when you send an acknowledgement,
right.
Yeah. But okay, here it's just we feel it's not too far. Okay. But we didn't do very elaborate. Okay. Now it looks promising. So this is the histogram of the backlog, and it also has a very nice. And when I saw this picture for a third time, I was a little surprised. Okay, it's really, it looks, it only would be much wider, but it's. Okay, so that's that. All right. So here's a summary. So what did we do? So basically, what I really try to do is to look at price-based rate control. Well, in order to motivate the approach that we use, okay, I use that game theory in the beginning to show that really this price is if you can set the price, that's all you have to do in order to do it. Okay? And we talk with this price, you can set stability and performance. And in order to set the performance, you don't need to know, and you don't need to know that. So this is kind of what I wanted to show. Also, all right. So this is what we did so far. Okay. Also, there's another thing. So these are the hard results. And the other thing we feel that this model actually, this two-dimensional Markov chain, it has to be very kind to us. Okay. So we try to do different things. Like we said, okay, so that's how we started. Really, we started with. I told that to Rich. We started with this rate control. Okay. And we got nice results. Then we said, okay, can we use this model to do a game theoretic analysis? Okay. So the first part came after this, and it worked. Okay. And we pushed it some more. We said, and then we asked questions, it gave us the answer. Okay. So somehow, also the model itself, there's some simplification and all that, but somehow it was quite nice to study this issue for this map layer together with Ray. So I could stop here, or I could talk about some more extensions, but maybe it's better to stop today. Yeah.
Yeah, as I noticed, your equation, everything also depends on the lambda. Lambda should depend on the cost or
this one here?
Yeah. How do you control the lambda?
Oh, with the price.
But the arrival arrives at the node. And so the nodes decide whether to accept the new packet.
Yeah, it's like a price-based rate control. You say, okay, if this is the current price, this is how many new packets you are allowed to accept. So you could translate that if you would like into a window-based or something like that. So the window tells you how many new packets. So this would kind of be related.
So it's the rate of accepted packets, not the rate of packets coming in general?
Yeah, so internally maybe you say, oh, I want to send a large file. Okay, so right now you can, or if you want to do that, you do very, yeah. So that's just, this gives you the rate at which you're allowed to inject packets, or pass packets down to the map layer. Okay. Which looks a little bit weird. Okay, it depends how you look at it. First you think, okay, whatever I have, I want to send. But I mean, TCP does something similar. It controls, the transport layer is between the application and the map layer, which tells you how many packets you are allowed to activate, and this does the same thing.
So, in the second problem we discussed is, in what sense is optimal? In what sense is optimal?
The second one?
Yeah, it is not supposed to be optimal.
It's not really. It's about design. Okay, you have a system, and you want to have a design in terms of throughput and delay. Okay. How can you?
That's considered, right? That's considered. For example, you can set the goal as balance of throughput and delay.
Yeah. So first of all, here what we did is can we control the network optimally in the sense that we get the maximum throughput e to the -1.
Okay. So
and that's you can do it by doing it this way.
Yeah. So in the second case, it can still be optimal.
In terms of you achieve the best maximum throughput.
The second question is the convergence. Is the convergence does a convergence depend on the arrival rate?
Yeah.
It depends, right?
Yeah, I mean, if the arrival rate is very steep, okay, and you're here and you make a small change in price, they will be. Yeah, I mean, the conversion is if you change the price a little bit, how we can change to have it all right.
That would be very. I mean, the definition of the rate is very important.
For the yeah. I mean, okay, that's what you could do. You could say, okay, you always
You can see that you throw away the assumptions of state n and lambda u.
Yeah.
But maybe I missed something. I kind of remember in the second problem, you're assuming that you have a uniform Q, right?
That's what I assume, yeah.
But the question is, well, you say you do not need to know. You just do not need to know the value, as long as they have a uniform.
Yeah. For the throughput, I don't need to know the value. For the delay, I need
but as long as everybody having the same Q.
Yeah.
But does that apply to a more ad hoc network, where, or a CDMA, CSMA CD, where they're doing exponential backoff, things like that? how that will apply.
Okay, that's an extension. Now you want to say different nodes when we have different delay requirements.
Then the similar result will hold?
Similar results will hold, yeah. I mean, that's what I mean. You can push it further, okay? You can say, can I have different delay requirements? Can I have delay differentiation? You can do it. I can say, can I also let the retransmission probability be a function of this price? Somehow the price captures the backlog. So if the backlog is very high, maybe the retransmission probability should be very small. Okay. Can I do that? You can do that. Okay.
In your first couple of slides, you mentioned CS and ACD. What about wireless LAN, CA, with the CA? Did you do any work analysis on that?
Okay. All right. That's my personal opinion. The CA is just, it's just a variation. That's how I see it. I mean, it's to get around the hidden terminal problem. So if you believe that how is it called? RTS. If that function has
the RTS, CTS, and the nav.
Yeah.
You didn't do work, but you truly believe they're pretty much the same in terms of this analysis.
Yeah, I mean, you see, you want to actually how is it called? RTS.
RTS, CTS.
So, yeah, I mean that's a nice mechanism to actually communicate the price.
Okay.
Actually, it would help, because you send an acknowledgement. You can.
Okay, so basically, you can throw away the first assumption that you're saying you have an AP. It doesn't matter if you have AP or not in this analysis, right?
It does.
Up to this point.
It does.
Up to this point.
No, it does. Okay. So here, okay. There's a way around it, but right now it does. Because if you don't have an AP, different nodes would have different starting prices.
So they have to follow the same mechanism of the U.
Exactly. But you can get around that, there's a way to solve that.
They cannot do that in a distributed way. There has to be a centralized.
No, there is a way to do it. This is decentralized, but again, you can say, can we do it distributed? You can do it distributed.
I'll slow you down.
Excuse me?
I'll slow you down until you see from.
I think it's not that much. Okay, it's not that much the convergence rate. You lose some precision in the performance. You cannot say anymore the performance is here, but you can say the performance is going to be in the wall.